Hello, this is John Miares, and in this lesson, we're going to start moving away slowly from our direct studies of trigonometry and begin looking at other pre-calculus oriented topics. This particular topic, the polar coordinate system, is not something that you're going to probably see again until Calculus 2, but it is something that will be good for you all to explore as we work to expand our minds in preparation for calculus. Granted, many of the ideas we learn in trigonometry are going to be used in these next two chapters, just not as intensely as they have been in the past three. Up until this point, we've dealt exclusively with the Cartesian coordinate system, or the rectangular coordinate system, or the XY coordinate system. However, this is not the only coordinate system that is out there, nor is it necessarily the easiest to work with for all types of functions. Coordinate systems are really nothing more than a way to define a point in space. In the rectangular coordinate system, a point is defined as the coordinates x, y, and we can use this to locate the point by starting at the origin, then moving x units horizontally, followed by y units vertically. This is not, however, the only way to define a point in two-dimensional space. The polar coordinate system gives us a way of plotting points based on a distance r from a point known as the origin, or the pole, and an angle of rotation, theta. The initial motivation for the introduction of this polar coordinate system was the study of circular and orbital motion of celestial bodies. As you can see on this graph, you've got things that look like your x and y axis, but instead of having a rectangular grid, you see a series of concentric circles here whose radii are each 1 unit further out than the other. We also have these lines coming out from the origin, again, which we're calling the pole now, that represent a particular angle of measure that was coming out of an angle in standard position. These are referred to as polar angles or azimuths. A-Z-I-M-U-T-H, azimuth. Each of the azimuths shown on this graph are 15 degrees or pi over 12 radians apart from each other. One possible way of thinking about these is to imagine being above the North Pole and staring down on the Earth. The latitude lines are going to represent our distance from the pole, while the longitude lines can represent the degrees of rotation. Let's look at how we might plot points on this type of graph. Suppose you were asked to plot the point A in the polar coordinate system, whose coordinates are 4, pi over 6. The first coordinate, the 4, is the r value, or the radial coordinate, representing the radius from the pole. The pi over 6 is the angular coordinate, which represents the angle of rotation, assuming we're using angles in standard positions. Sometimes when we're plotting, it's going to be easier to measure the angle of rotation before we try to consider looking at the radius. As I noted earlier, each of these angles, or azimuths, angle bearings, are going to be 15 degrees or pi over 12 radians apart from each other. So pi over 6 is going to be the second azimuth above what used to be the positive x-axis. With r equals 4, we're going to go out to the fourth concentric circle here, 1, 2, 3, 4, and that is going to get us this point right here. Let's try another one. What if we wanted to plot the point 3, 0? Then what we're going to do is go out 3 units from the pole, but not rotate any measure of an angle at all. That's going to land our point B right here. Now this one's a little different. How might we plot the point -2 comma 5 pi over 3? When we're working with the ideas in trigonometry and reference triangles, the r value always has to be positive. But here, we're going to allow for a negative r value. If the r value were positive 2, well, let's go over to where 5 pi over 3 would be. 5 pi over 3 would be 300 degrees, so we're going to go around 90, 180, 270, 285, 300 would be along this azimuth here. If the r value were positive 2, I would be right here. However, in order to go to -2, what I'm going to do is I'm going to back up and go 180 degrees in the opposite direction, and I'm going to end up at this point right here. So really what it's like is if we were heading down the bearing of 5 pi over 3, which again is normally in quadrant 4, and then turning around and going in exactly the opposite direction out the 2 units that we were going to go otherwise. Why don't you try the next 3 on your own? Pause this video and see if you can figure out where you should be plotting points D, E, and F, and we'll regroup in just a bit. So for point D, negative pi over 3 is going to be coterminal with 5 pi over 3 in the fourth quadrant. It'll be this azimuth right here. The r value is positive 5, so we're going to go to negative pi over 3, or negative 60 degrees, and then go 5 units out on the circle, which will put us right here. For 0 comma pi over 4, well, pi over 4 is this third azimuth coming out of the pole in the first quadrant. However, we have a radius of 0, which means that we're really not going anywhere from the pole. So our point ends up being right here at the pole. For the point 6 comma 3 pi, we first want to go to 3 pi radians. Now, 3 pi radians is equivalent to 540 degrees, which will be 1.5 full revolutions. Essentially, we're landing on the negative x-axis here. We'll travel out 6 units, and we will end up right here. Let's take a second look at some of these points again before we move forward. From this sketch, we can see that if r is positive, the point is going to be in the same quadrant as theta. On the other hand, if r is negative, then the point is going to end up in the quadrant exactly the opposite as theta. Notice that as well, if I asked you to plot the point 2 comma 2 pi over 3, we would end up in exactly the same place as we would for point C, whose coordinates were -2, 5 pi over 3. For the point 2 comma 2 pi over 3, we would be expected to rotate an angle of 2/3 pi from the positive x-axis and then move out 2 units along that azimuth from the pole. This leads to an important difference between Cartesian coordinates and polar coordinates. In Cartesian coordinates, there is exactly one set of coordinates for any given point. With polar coordinates, that is not true. In polar coordinates, there are literally an infinite number of coordinates for a single point. For instance, the point -2 pi over 3 could be written as 2 comma 2 pi over 3, or if we get creative, we could represent this as 2 comma -4 pi over 3, or -2 comma -pi over 3. Why don't you try this with point D on your own? Try to find three alternative sets of coordinates for point D. Pause this video and see what you can come up with. So here are the three that I might be comparing with point C that we did earlier. Option one might be to say that point D is going to be at 5 comma 5 pi over 3 because I know that 5 pi over 3 is coterminal with negative pi over 3. If we wanted to try to use negative 5 as the R value, we could use negative 5 comma 2 pi over 3. Or if we measured our angle in the negative direction, we could say it is negative 5 comma negative 4 pi over 3. So the easiest way to find these angles is really to look for just coterminal angles, which are always separated by 2 pi radians or 360 degrees. When working with negative radii, you're going to have to go with angles that are 180 degrees or pi radians in the opposite direction from the initial bearing of angle theta. Then anything coterminal with those is going to work. Now let's talk about how we might convert a set of coordinates written in polar notation to their equivalent in rectangular notation. If I was to think about how we're going to do this, we want to consider the relationship between r and theta as they compare to x and y. Let's say I was to look at point A here, for example, which is 4 units out from the pole on an azimuth of 30 degrees or pi over 6 radians. The x and y values can always be constructed by drawing a reference triangle. We know that the angle is pi over 6. I know that the hypotenuse is going to be 4. The x value would be the adjacent side of the reference triangle, which we could compute by considering the cosine of angle theta equals x over r. Rearranging that equation can get us that x will equal r times the cosine of theta. Similarly, the y value can be represented as the opposite side in this reference triangle over the hypotenuse r, which after we multiply by r will give us y equals r times the sine of theta. So now let's say we actually wanted to convert the coordinates 4 comma pi over 6 from polar into rectangular. For x, let's take the r times the cosine of theta, which becomes 4 times the cosine of pi over 6. The cosine of pi over 6 is the square root of 3 over 2, which if we multiply that by 4 will give us 2 square roots of 3. For the y value, let's use the conversion y equals 4 times the sine of theta, which when we substitute will get us 4 times the sine of pi over 6. The sine of pi over 6 is 1/2, which when multiplied by 4 will give you 2. So that tells me that the location of point A, which had polar coordinates 4 comma pi over 6, can also be represented in rectangular coordinates as the point 2 square roots of 3 comma 2. Why don't you try this one on your own? Let's look at point C and see if we can determine what the corresponding x and y values are associated with this point. Go ahead and pause this video and we'll see what you come up with in a bit. Again, we could draw a reference triangle, dropping a perpendicular from point C down to the nearest x-axis, and then formulating a reference triangle. Since the cosine of the angle is x over r, we can compute the x value by taking r times the cosine of theta. Now, do we need to worry about the fact that r is negative here? No. We can just substitute in what we know, that r equals -2 and theta equals the cosine of 5 pi over 3. Remembering our mad minutes, the cosine of 5 pi over 3 is 1/2. So -2 times 1/2 will give you -1. To get the y coordinate, we'll use the other conversion formula, y equals r sine theta, which, substituting in, is going to give us -2 times the sine of 5 pi over 3. The sine of 5 pi over 3 will be the negative square root of 3 over 2, which, when we multiply that by -2, gets us the square root of 3. So that means that the rectangular equivalent for the point -2, 5 pi over 3 will be the point -1, square root of 3. Now let's talk about what we would need to do to take a set of rectangular coordinates and convert them to polar. With rectangular coordinates, we have the x and the y, and we'd have to work to translate those into r and theta. Unfortunately, the same conversions we used before aren't going to work here, but we do have other options. We know that from the Pythagorean theorem that x squared plus y squared equals r squared. So we could rearrange this to get r equals the square root of the quantity x squared plus y squared. To evaluate theta, that's going to be a little more challenging. What we know is that the tangent of theta is going to be y over x, since y represents the opposite side of our reference triangle, x represents the adjacent side. In order to solve for theta, your first instinct might be to simply take the inverse tangent of y over x, and that will give you one possible answer. However, what it will give you is a reference angle, not necessarily the correct angle measure that you're looking for. As was discussed a couple of different slides ago, there are literally an infinite number of ways that an angle can be represented here based on whether you want to go with something coterminal or you want to see a negative r value. So what I would strongly recommend is that you always draw a quick picture to check for reasonableness of the placement of your angle before you submit any final answer. Let's say we wanted to convert the points 4, -4 and 0, 6 from rectangular form to polar form. The first thing I would recommend is to plot these points on a graph. 4, -4 falls in quadrant 4, while the point 0, 6 is on the positive y-axis. Our challenge is to determine what this means on a polar coordinate system. Let's start with the point 4, -4. If we say that the tangent of angle theta is y over x, -4 over 4, this will reduce to just -1. That would mean that angle theta could be -pi over 4, which, when looking at this graph, seems reasonable. The r value we'll get by applying the Pythagorean theorem, which will give us the square root of 32, which will simplify as 4 square roots of 2. So we could write our answer as 4 square roots of 2, -pi over 4. However, let's say the instructions on the homework problem say we needed to find a value of theta that falls between 0 and 2 pi radians. In that case, we'd have to go with an angle coterminal with that, which would get us up to 7 pi over 4. For the point 0, 6, let's start with the same approach. The tangent of theta is y over x, which is 6 over 0, which is undefined. For some of you wondering what to do with this, there's a few things to remember. Looking at the graph of the point 0.06 up here, it lies on the positive y-axis, which is at 90 degrees or pi over 2 radians. And if you recall from your math minutes, the tangent of pi over 2 is undefined. So this is going to work out just fine for us. We'll just have theta being pi over 2 radians or 90 degrees. Now for r, we'll again use the Pythagorean theorem, which boils down to the square root of 36, which will just reduce to plain old 6. This is another one where we could have probably used some common sense to compute the value of r. Remember, r represents the distance of the point from the pole. And looking at it, the point 0.06 is 6 units directly above the pole, so it should seem reasonable that r is going to equal 6. So the coordinates of the point 0.06 when converted to polar notation could be written as 6 comma pi over 2. But again, there are other angles coterminal with pi over 2 that we could use, like negative 3 pi over 2 or 5 pi over 2. If we said r could be negative, that would allow us to use negative 6 comma negative pi over 2 or even negative 6 comma 3 pi over 2. Now let's see what happens if we consider converting entire equations from rectangular to polar form. Here are just a few that we're going to look at. Y equals 4, 5x plus 3y equals 4, and x squared minus y squared equals 2y. These first two are just straight lines. Y equals 4 is a horizontal line, and 5x plus 3y equals 4 is a diagonal line with a slope of negative 5/3. The third equation, if you're to rearrange it, is actually going to be the equation of a hyperbola. You may be able to recognize it from the pattern of the x squared minus the y squared. When doing these conversions, we may need to pull in any of the 4 conversion equations that we've already discussed when changing points from polar to rectangular or rectangular to polar. For the first example, y equals 4, we'll want to use this second equation in our list, which says that y equals r sine theta, and substitute that for y in our equation. If possible, we want to try to convert this equation into r equals form. Doing this means dividing both sides by the sine of theta, which then, if we apply the reciprocal identities, will get us r equals 4 times the cosecant of theta. In the second equation, 5x plus 3y equals 4, we're going to have to use both the first and second conversion equations and substitute x equals r cosine theta and y equals r sine theta in there. Now we've eliminated the x and y's, but how do we turn this into r equals form? Let's factor out the r as a common factor out of the first 2 terms, which will give us what you see here. Then we can divide the quantity in the brackets, which will get us r equals 4 divided by the quantity 5 cosine theta plus 3 sine theta. And that would be our final answer. For the third example, we're going to try a similar approach, but the results are going to be a bit more messy. We know x equals r cosine theta and y equals r sine theta. So we can substitute those everywhere we see x and y, which will get us what you see here. Squaring out each term on the left side of the equation and factoring out a common factor of r squared gives us r squared times cosine squared theta minus sine squared theta equals 2r sine theta. Now, the cosine squared theta minus the sine squared theta, we can turn into the cosine of 2 theta based on a double angle identity. I could divide out on both sides by the cosine of 2 theta, and then divide both sides by r, and be left with r equals 2 sine theta cosine theta, which will have a final answer that looks like this. Now let's look at what we would do to convert an equation from polar form to rectangular form, starting with something that has r's and thetas and turning it into something with just x's and y's. For the first equation, r equals 3, we could start by using the Pythagorean theorem here, but then we would want to square both sides to clean this up, which would give us x squared plus y squared equals 9. Now, if you recall from our studies of conic sections at the start of the course, this equation will represent a circle with a radius of 3 centered at the origin. Thinking about the polar form, what we're coming up with is a function that represents all points that are a 3-unit radius from the pole, which if you think about it, will be a circle. For the second equation, you've got theta equals pi over 3. Knowing our equation for conversion here says that the tangent of theta equals y over x, perhaps what we can do is take the tangent of both sides of this equation, so we have the tangent of theta equals the tangent of pi over 3. Well, the tangent of pi over 3 is the square root of 3, and the tangent of theta from our identity is going to equal y over x. If I multiply both sides of this equation by x, we'll end up with y equals x times the square root of 3. This equation is going to represent a straight line with a slope of the square root of 3 and a y-intercept of 0. For r equals 2 sine of theta, we're going to have to get a little more creative. We have a conversion factor which says x equals r sine theta. But what we have here is r equals 2 sine theta. If we had an r in front of the sine theta right here, it would be pretty easy to convert. So a trick we're going to use is to multiply both sides of the equation by r, which will give us r squared equals 2r times the sine of theta. Now we have two identities which can help us with our conversion. On the left side, we have r squared, which will equal x squared plus y squared. And on the right side, we can replace the r sine theta with a y. We can recognize this as a conic section of some type, so we should try to move everything to the left side and perhaps try to complete the square. Half of negative 2 is 1, and 1 squared is 1. So if I add 1 to both sides of this equation, we can complete the square for y, and we'll get x squared plus the quantity y minus 1 squared equals 1. This equation, if you recall from the start of the course, represents a circle with a center at the point 0, 1 and a radius of 1. Now again, for some of the problems you see on the homework, you may not be expected to simplify it quite this far. However, as we are starting to get closer to the final exam, I thought this might be a good opportunity to provide a little review for some stuff that we haven't looked at in several weeks. Let's look at one more of these. Here we have r equals 2 over the quantity 1 minus the sine of theta. Again, without the r in front, it's hard to do anything with just the sine of theta by itself. But we could cross multiply here, which gets us r times 1 minus sine theta equals 2. If we distribute, we will get r minus r sine theta equals 2. Now, if we substitute some of our conversion equations, we'll get the square root of the quantity x squared plus y squared minus y equals 2. It would be nice to clean this up a little bit, and your first instinct to do so would be just to square both sides. But we can't do that until we isolate the radical on the left-hand side. So if we move the y to the other side of the equation and then square both sides, what we'll get after we expand is going to be x squared plus y squared equals 4 plus 4y plus y squared. Again, you may recognize this as the equation for some conic section. So let's move everything back over to the left-hand side to see what happens. If I subtract y squared from both sides, they cancel out completely, leaving me with x squared equals 4 plus 4y, which we could factor a 4 out and get something that looks like it will follow the pattern for the standard form of a parabola that will open upward with vertex 0, -1 and have a p-value of 1. Again, I don't believe that you will be expected to take it this far on your WebAssign homework in Chapter 8, since technically the textbook doesn't cover these until you get to Chapter 11. But since we did Chapter 11 first, and these are going to show back up on the final exam, I thought this was something that was worth a review. Now let's talk about how one would graph these equations in polar form. How we graph these is going to differ between the different graphing utilities. So I'm going to start by showing you what you need to do on Desmos. Let's say I asked you to graph these particular equations here, most of which we've already looked at in previous examples in this presentation. Once you open up a new graphing window in Desmos, you want to click on that little wrench in the upper right-hand corner. There's going to be an option to change your graph from rectangular mode to polar mode right below where it says grid. Selecting this option will give you something like what you're going to see to the left here that I can zoom in and zoom out of to get the ideal viewing screen. Let's look at these equations one at a time. R equals 3 will give you a circle centered at the pole with radius 3. Theta equals pi over 3 cannot be graphed directly in Desmos because it will only allow you to write equations in R equals form. If I want to graph this in Desmos, I would have to convert this equation into its rectangular equivalent, y equals x times the square root of 3. The next one, r equals 3 cosine 4 theta, is kind of a cool spirograph looking like shape. Each of the petals will be 3 units out from the pole, and the tips of the petals will be 45 degrees apart from each other. For the fourth equation, we're going to have that parabola opening upward with a vertex at 0, -1. The final equation we didn't look at earlier, but it gives us a really cool looking shape as well. Now, I'm not going to ask any of you at any point to know how to graph these by hand or know any of the special names of any of these fancier shapes. You're not going to be dealing much with polar coordinates and their applications until late in Calculus 2, and if the technology can do these out for you, that's going to be much easier to work with. Our graphing calculators have the ability to graph polar equations as well. The first thing we're going to have to do is set our calculator mode to handle polar equations. So I'm going to press the mode button and I'm going to scroll down here to where it says function, and then I'm going to hit the right arrow until I get to where it says polar and hit enter. Then I'm going to hit zoom trig. Since we're working primarily with trig functions here, and then I want to check my window settings. Let me hit the window button here. Notice that what you're going to see, we have different values here for x and y that are setting on our window. However, we also have these things for theta min, theta max and theta step. That is going to be something that will help us as we're going to trace on these graphs and look at points with respect not just to x, y, but in terms of r theta. Now, when I press the y equals button, you should notice that I don't have the standard equations y1, y2, y3 that I normally would have, but I have R1, R2, R3 through R6 that are listed here. This is going to be typical if I have my mode set in polar form because I will want to enter equations that R equals some function of theta. So here, let me enter in the four equations that we were working with here. So we had R equals 3. I'll say R2 equals 3 cosine 4. And notice if I hit this button x comma t comma theta comma n, I'm going to get a theta when I'm in polar mode. If I was in parametric mode, I'll get the letter t, and we previously explored sequence mode. If I press that, you're going to get the letter n. The next equation I'll look at is 2 divided by parentheses 1 minus sine theta. And I'll double close my parentheses here. And then the last one I'll look at is r equals 3 plus 6 sine theta, like so. Now, when I hit the graph button, when I do that, I see what's supposed to be the circle. Here comes that parabola. Notice how it drew it in a really funny order. That's because it's plotting it from theta equals 0 up to theta equals 2 pi, and that isn't necessarily going to graph it from left to right. Now, another thing you should notice is that this thing that's supposed to be a circle with radius 3 doesn't really look like a circle. It looks a lot more like an ellipse. So what I'm going to do here is I'm going to hit zoom square, and that should give me a window that is looking a lot more proportional. So my circle actually looks round. Let's look at this parabola again as it's drawing. Notice again, it's not graphing it from left to right. It's starting where theta would equal 0, and then as it's going around to theta equals 2 pi, that is where it's going to show essentially the path and the order that that graph is going. So just to summarize, again, we want to make sure we're setting our mode to polar mode. Then we'll hit zoom trig in order to set the window initially because what we're working with are primarily trigonometric functions. We'll make sure our window looks reasonable. It's going to range values of theta equals 0 up to theta equals 2 pi. I've entered my different equations in here. I can't enter the equation theta equals pi over 3 because I don't have that ability to do so here, but that's really not that big a deal. And again, the calculator will give us our four different graphs, which if I wanted to clean those up, all I would have to do would be to hit z square. All right, so I hope what we've covered here is something that you found a bit interesting. It's a bit different from what we've done so far, but I'm not intending to do anything particularly intense with these polar functions in this course. You're not going to see these again until you get to the end of Calc 2. So the purpose of looking them here is just to give you a little bit of exposure to them. So when you do see these later in another course, you will be open to the idea of working with different coordinate systems other than just the rectangular coordinate system and XY points. It is also a nice little extension on our study of trigonometry here because in order to convert from xy coordinates into r theta coordinates or even entire equations, we have to use our identities which relate x, y, and r to each other, and then you'd have the sine of theta being y over r, the cosine of theta being x over r. Here are the problem challenges for sections 8.1 and 8.2. Most of these problems can go pretty quickly, And a lot of these problems you can probably do directly on your calculator. So I don't believe it will take you too long to get through these. As always, if you have any questions or any worries about these problems, feel free to contact me via email or post your question on a discussion board. Thanks for watching, and we'll see you all soon.